Good afternoon, everyone. Hope everyone's doing well. Glad to see some familiar faces. Like Tanya said, I think this is pretty informal, so if you have a question, pop it in the chat. Feel free to unmute at some point. I don't have a ton of slides, so this will be more of a discussion as well, not just a information dump. So hopefully this will give you some insight into the model and some new developments that are funded through CIRP as means to kind of answer some of the statements of need that were highly ranked in the research area review group. So I call this talk Bridging the Gap between Shallow to Deep Water or Shallow to Intermediate Water, because if you know something about waves, specifically in our regime, Coastal Hydraulics Lab, those waves are either deep or they're nearshore shallow, right? There is a gap in between. And operationally speaking, we've always struggled with connecting the two. Not only just saying when two models or two disparate models should talk to one another, but there's a lot of physics questions in between. There's a lot of pieces that are missing when you're trying to couple from one model to the other. So with that said, there's been attempts to try to push models oftentimes outside of its regime or further just push the envelope to see if they can run on larger domains, longer domains, as well as more complex domains. And that includes oftentimes deeper water that it's not conducive to the original derivation of the equations. So I'll give you first a little bit of a poster slide. Hopefully I can advance this. Too many screens at once. If you're not familiar, I'll spend a few minutes here talking briefly about what the model is. It's got quite a history through different versions of it, going back to essentially 1995 for the sets of equations, nonlinear sets of equations, and then pushing it to its first release, FunWave 1, to 1998. So the model is quite old, had different versions, and the FunWave, as we now call it, FunWave TVD, total variation diminishing, goes back to 2012. What you can think here is that FunWave does not mean it's a fun model to run. Everybody tends to ask that. It's a fully nonlinear fully nonlinear wave model, because in 1993, its predecessor, let's say Boost 2D, if you're familiar with it, had weakly nonlinear sets of equations. So 95, 2 years after, it only made sense to call it fully nonlinear. It's a model that's applicable in the nearshore, and what I mean by nearshore, I'll explain on the next slide in a little more detail, but we're calling it shallow to intermediate water. Okay, it's a phase resolving model. So when you're standing on the shoreline, if you're viewing that animation on the bottom right, hopefully it's coming smooth. I know sometimes animations are getting choppy when we're doing webinars. That itself means that you can follow a wave or a series of waves by standing on the beach and essentially looking at every individual crest and trough if they're non-dispersive, okay? What else? The model itself has been co-developed through us, CHL, and the University of Delaware for a good portion of the last 7 to 8 years. It's an open source code. Okay, it has a BSD2 license, which is loosely, we call it copy left, not copyright. What that means for you is that if you ever want to take that code and use it and develop some additional modules, you have the freedom of closing, okay, the additions that you develop while keeping the original code the same. So for the purpose, say, of military engineering applications where you may not have the capacity to share the code, you can add different features into the model, as in fact we're doing now with some of the work we do for the Defense Threat Reduction Agency for underwater explosions, that there are pieces that may not be fully available open. But to give you a glimpse into some of the capabilities of the model, we're talking about things like nearshore wave propagation, transformation, that also includes refraction, diffraction, and linear shoaling. For your information, those things that are underlined in bold here are not readily available from a physics perspective in phase average models. And those pieces in parentheses in blue are sort of comparisons, or how you would maybe look at these features from the military perspective, right? So additional things that are common here that are well resolved: bottom friction, wave-induced current, nonlinear wave interactions, but also wave breaking through different mechanisms, which directly influences run-up and overtopping of structures. So a lot of work that we all do across our wide flood risk management business line is that piece of flooding and flood risk management. We've also done a good chunk of work with harbor resonance and excitation of long waves and harbor tranquility. So we're talking about infragravity IG waves. For the last few years rather, there's been an increasing interest in vessel-generated waves and what those do for the adjacent environment. So we're talking about sediment transport and morphology change. And I'll show you some slides as we go forward. In addition to that, we've done work for landslide-generated tsunamis, whether they are seismic events or some underwater detonations. And finally, I just want to bring your attention to two pieces. And I mentioned earlier that the model is being used across wider, larger domains. Now we have multi-grid nesting for flexible grids, including also the development and implementation and release of a high-performance computing portal, which is a GUI, if you can think of it that way. So let's move on to the meat of this presentation. Trying to advance a slide. Okay, there it is. So the motivation for the current work in the context of CIRP, Coastal Inlets Research Program, was really a threefold. I alluded to it several times, but let me say it again. First, FunWave is being applied to increasingly more complex domains, and that means larger domains in terms of space and also with time. Simulations across a few minutes, few hours no longer happen. Sometimes we're doing things across multiple days, and as you know, with that, variable water level is an important piece to be added. Yes, in the open coast, we may run applications where we have a constant static water level and we reset applications from one to the other, sort of hot start. But when it comes to other areas, say in particular inlets, that's no longer sufficient. You have to also look at the input from surge and tide in terms of currents, tidal currents, and how they interact with wind waves and vessel generated waves too, not just in the context of depth limited braking for run-up and overtopping, but also sediment transport itself. So the other third piece here is that pretty much all second order boussinesq type models, and here we're talking about FunWave, CoolWave, Boost2D, BOSC, and many of its friends, those models are weakly dispersive. So the takeaway from here is if you look at the schematic to the right-hand side, you see the individual distance between the horizontal distance between two crests. Not sure if you're seeing my mouse, but I'm going to try to point to the big red L. That's a wavelength. And then correspondingly, the depth, undisturbed water depth, H. When it comes to the ratio of H over L, okay, that is a driver, or you can look at its sort of a simplification of K times H, wave number times the depth. That value itself has to be less than pi. And I'll come back to it. But what that really means is that wavelengths have to be, for these models, to even have a chance at resolving these waves, those wavelengths of interest have to be at least twice as big, twice as long as the depth, right? Because anything beyond that goes into the regime of deep water, okay? So the work that we're undertaking in this effort is one, to have a variable water level through a single simulation, and two, ultimately have, I'm going to use it in air quotes, a more dispersive model, a model that deals better with deeper water or shorter waves equivalently. And one other piece, maybe a little technical, but it is technical talk discussion, so I'm going to throw a few things at you. In the context of a pretty hot topic, an area that nowadays is receiving a lot of attention, and not just confined channels, but in other sort of coastal environments, is vessel-generated waves. Not just through large container-type ships, but also from fast recreational vessels, which oftentimes are on track because they're not required to have any GPS transponders as they're moving through. So it's rather difficult sometimes to quantify their effects. But here is an example of an actual tangible example using a spectrogram analysis, what this KH less than pi, or weakly dispersive, or third definition, as I was calling it on the last slide, the waves feel the bottom or wavelengths needing to be at least twice as long as the depth. Here's a time series on the top left of two vector devices in the water, red and blue, kind of seeing it here on the video animation, and looking at a spectrogram analysis where here in the vertical axis you've got frequency and a horizontal axis you've got time. You can look at different energy density spectra in specific regions and attribute that to sort of connected or disconnected components of a wave spectrum here. From looking at an episodic event, you can't just take traditional FFTs because it's a different non-stationary problem, but you can do different moving transforms, including here a spectrogram by spectrogram analysis. The point here on this is that on the right-hand side, you've got different pictures, different images of individual wave trains captured. Okay, hopefully you're seeing those blue. Hopefully this is large enough. And correspondingly, the spectrogram analysis, the spectrogram plot, again, frequency versus time, looking at that along the curve, which we call a dispersion curve. The big message here is that many of these are within the regime that FunWave can resolve. But if the energy falls above this sort of aura pink line, KH equal to pi, the model, second order boussinesq model, does not do well at all resolving those waves. In other words, they're propagating as if they were non-dispersive, whereas they should be propagating as dispersive waves. So in those examples that you see here, when the energy, peak energy, majority of the energy falls above this KH equal to pi, models like FunWave and many others who will have potentially a boussinesq type model as an engine, but then they're adding a vessel-generated waves into it, they will be failing in these sort of shortwave regimes. So hopefully this gives you enough motivation. I'll pause for a moment in case I missed anything in the chat, or if there are any questions. Okay, hopefully I gave you enough to hit the unmute button. Let me progress. So, we talked about the need number one. The need number one, you're seeing actually it being used in a real simulation. This is an example of Hurricane Irene near Willoughby Bay, pretty much Norfolk area north of our FRF facility. This is specifically looking at run-up, okay, and obviously overtopping if it occurs, subject to surge type forcing, okay, forcing on the boundary. So the interesting piece here is that hopefully you can track this red dot here. I know these video animations, well, they're looking great on my end. Sometimes it's a challenge on the video. But the message here is that you can begin to look at these events, okay, especially when there's a large surge coming, in a longer domain, in a larger domain that is conducive to your actual input values. Let me give you another example. Hopefully this is moving across as well. So what you're looking at here is, again, a simulation with the tidal and surge forcing, as well as irregular waves in the offshore, coming from a 100-year storm condition in South Bethany Beach area in Delaware. Okay, this boundary condition comes from the technical report from the inside, right, from ERDIC CHL. So you're looking here at the inundation, coastal inundation, across those domains. What I should probably mention is that with all this, there are different modules in FunWave, including a tracer module or particle tracking module, that in the context of putting everything together, surge, tides, waves, all within one module, physically resolved, you can also add different amounts of tracers, seeing where different debris goes if the flooding occurs. Let me move on to the next slide. Okay, so a little bit of detail as to how that is done behind the scenes, okay? The initial implementation I mentioned originally has been captured in both the technical note that's currently being reviewed. It's in peer review, but also it's already published on the wiki. If you Google FunWave Wiki, you'll go to the main website and you can search whatever you want, including a quick search, and I'll show you a snippet of that later. So this implementation is now currently in FunWave, in the original FunWave TBD. But as we move towards a deeper version, and again, using that in quotes, not a fully dispersive, but I'm calling it that for the sake of argument, we will also add that feature in terms of variable water level throughout a single simulation into that module. So this particular example, if you're catching it, has a moving boundary on the left-hand side. If you're looking at a cross-section right here, it goes from 0 to 1 meters, whereas on this side, on the right-hand side, it goes from 0 to -1. As a simple example of what this looks like, it has regular waves being generated on the inside with an internal wave maker. Okay. All right, so let's jump into two types of wave makers. Excuse me, not wave makers, but tidal surge module forcing types. The first one, we call it low pass sponge. It's an absorbing sort of a boundary layer where it must be placed anywhere you want. Okay, I'm being funny here, but for a moment, when I'm saying must be placed anywhere you want, means it has to be placed on the boundary. We've got something called a west and an east and a north and a south boundary. These have no correlation to geographical coordinates, but just a local domain in FunWave. So because we're using an internal wave maker, you can put this absorbing low pass sponge boundary condition that allows you to input both the surface elevation essentially and current or velocity on 1, 2, 3, or all 4 boundaries. Simple setting, you have two options. You can say that the tidal boundary condition absorbing is true, and you have an option between being a constant value, and here I'm just using east and west as an example. You can put the steady number or a constant number, or you have a data type that is data, right? If you don't put constant, if you put data as one of your types, you have to add or you have to supply 2 files or however many times, excuse me, however many sides you are imposing your surge and tide input based in terms of tide west file, tide east file, etc., etc. So here's an example of what that file looks like. It's a generic time series that gives you a time of the tide. It gives you the value of the surface elevation and gives you U and V, right? So these are velocities in the X and Y direction. Of course, if you're familiar with boussinesq models, one of its benefits is the fact that it's not a three-dimensional model. Some call it the depth average, but it's one of those models that has been expanded about a reference depth, okay? So you are able to provide this very important current, tidal current, which inevitably influences the transformation of waves, but also influences the depth-limited braking and subsequently sediment transport in that context. So you can give it a time series, okay, on both, on all, on one, on all sides. But again, oops, somehow we jumped one slide. Let me come back. Again, let me reiterate, you do have to provide an internal wave maker on the inside for this type 1. Okay, so let's move on to type 2. Type 2 does not require you to have an internal wave maker because what we call it is an absorbing generating boundary condition. The caveat here is that because it is both absorbing and generating, this generation has to occur on left-hand side. And I'm saying left for 1D, or in a true 2D simulation, we can say it occurs on the west side, right? So there are some benefits in the context of when do I use one or the other, depending on your application. But here's an example, right? Wave maker type, you call it absorbing generating. you give it a data type, you can actually provide a wave comp file that gives you an ability to provide a two-dimensional frequency directional spectra directly into your wave data generator. And then you've got the tide piece itself in the very same fashion as on the previous slide, where you've got the time series, you've got the surface elevation, and correspondingly, if you want, U and V, tidal currents, right? So here's just a schematic of what this looks like in a 2D, very, very simple domain, just to give folks an idea of what this looks like in terms of a moving water level, and then subsequently irregular waves that are driving this, okay? So lastly, let me mention, because it's an important piece as we spend a good amount of time trying to update all of our communication, is that I would encourage you, if you're interested, to go visit our model wiki, not just to get more insight into this particular problem, this particular feature, but there is a whole bunch of other pieces if you even want to learn about the model, if you want to use it in the HPC portal, which is that nice interactive GUI that we have being done through essentially our HPC services, high performance computing. But you've also got a ton of material for self-paced tutorials that I would like to encourage you to come visit if you're ever interested in the model. So let me kind of wrap it up with a current work, or work in progress, as we call it. Concurrently, we're spending quite a bit of time on looking at quality control in terms of robust user interfaces. So I mentioned a few times the high performance computing and other entities are trying to help us with that. Efficient input and output system for massively parallel machines. This kind of goes back to larger simulations, longer simulations require a ton of output, and now we're noticing that the time it takes to write to a file is becoming more and more of a problem. We do have parallel ability to write. In other words, each individual core or processor, if you may, writes to a data file, writes to a specific location in memory. But then we're also noticing that this is impacting our synchronous communication, and I'm using that terminology of message passing interface. So if you're not familiar with it, don't worry about it. But we're looking at an auxiliary node to essentially be given a job of writing things to a file too. There's also a good amount of effort looking at pre and post-processing packages, most of them written in Python, so they can be used throughout different frameworks, whether it's the portal, whether it's the new development of the SMS system that's going to sort of infuse FunWave into it and release it as an open product. And I know Chris Massey's leading some stuff, including some of our work to help it to talk and drive and communicate with larger frameworks, say like CStorm, for instance, when you have areas of interest and you want to compute waves in a higher fidelity in that effort. And lastly, just coming back a full circle, the work is starting on extending the model into, again, loosely, as I'm going to call it, more dispersive, shorter versions, so we can actually drive the model not just to deeper water in a coastal environment, but more specifically, probably more so about vessel waves, resolving a longer wave train or a true full energy wave train in 2 dimensions in confined waters, that those waves are propagating across deeper and deeper channels. So I'm gonna just throw this out there. I'm not gonna go into any backup slides. I think it's probably good to have a 25, 30-minute presentation so it doesn't take up too much of your day. But I wanted to just mention again, if you're in town, or if you're available rather, July 25th to 27th, we're holding our 6th FunWave workshop at University in Boston, Northeastern University. The info is out there. Feel free to contact us. I would love for you to be out there, and I would love for you to become part of the group. So I'm going to close with this slide. If you're ever interested in learning about the model or coming out to the workshop and becoming a member of one of the 2 to interact with you. All right. Thanks for your attention, and I'll turn it back over to Tanya.